As cars have developed, their electrical systems have undergone a series of transformations due to the ever-increasing items of electrical equipment they incorporate, specifically lighting, windscreen wipers, fog lamps, headlamp wipers, electronic ignition, window winders, door locking systems, instrument panel or control systems, heated rear window, rear windscreen wiper, and for Fiat, City-matic. On a modern car, the total electrical system appears complicated. A series of cables, some hundreds of meters long, run from the engine compartment to the dashboard and on through the passenger compartment to the luggage compartment. By examining the system function by function, it's easy to carry out the various checks needed to locate any faults which may arise. This sequential type of fault-finding approach is also adopted by the designers of modern diagnostic and testing instruments. To understand the qualities and values indicated by the measuring instruments, we'll first examine the physical laws governing electrical and magnetic phenomena, the makeup of the various electrical components fitted on cars, and the principles on which they work. Matter is made up of extremely small particles called atoms. Atoms comprise a very small nucleus and a certain number of particles which revolve around them. The whole atomic structure is reminiscent of an infinitely small solar system, with the nucleus occupying the position of the sun and the orbiting particles the planets. The nucleus of an atom is made up of electrically neutral particles known as neutrons and positively charged particles known as protons. The particles orbiting around the nucleus are electrically charged and are known as electrons. The atom is stable when the number of electrons in orbit is equal to the number of protons in the nucleus. Sometimes orbiting electrons are displaced, and the atom loses some of them, thereby becoming positively charged. In this case, we speak of a positive ion. An atom may also acquire electrons, thereby becoming negatively charged. In this case, we speak of a negative ion. In a material such as metal, there are a large number of free electrons drifting around on random trajectories. When free electrons, driven by some force or other, take on an ordered movement in a given direction, they give rise to an electric current. In fact, an electric current consists of the ordered movement of electric charges, electrons. The intensity of a current is measured by the amount of electrical charges in movement in a given period of time. The unit of measurement is called an ampere, the symbol for which is capital A. When the electric charges are moving in one direction only, the current is said to be direct. When, however, the movement of charges occurs first in one direction and then in another, the current is called alternating. The total time between the moment when the charges start to move in one direction and the moment they return is defined as a period. Since the to and fro movement of alternating current in relation to the passing of time can be shown by a sinusoidal curve like the one shown, it's defined as sinusoidal alternating current. On a car, the alternating current generated by the alternator is immediately rectified so that it can charge the battery. The battery supplies direct current to the car's entire electrical system. When a material is made up of atoms in which the orbiting electrons can easily be made to move, the material is said to be a conductor. If it has variable properties, it's said to be a semiconductor. On the other hand, if it's difficult to get the electrons to move, the material is said to be an insulator. Solid conducting materials are generally metals. The most efficient conductor is silver, but the most widely used is copper for reasons of cost. Liquid conducting materials are generally solutions of special chemical products in various liquids. For example, solutions of salts or acids in water. These salts or acids enhance water's natural conductivity. The resistance offered by various materials to the passage of electric charges is a measurable physical quantity. The unit of measurement for resistance is called an ohm, and the symbol for this is a large omega. Resistance depends on the type of material through which the current flows. It's directly proportional to its length. That's to say, the longer the conductor, the greater the resistance. It's also inversely proportional to the cross-section. In other words, an increase in cross-section results in a decrease in resistance. The resistance offered by a material through which the current is flowing produces heat in proportion to the amount of current and to the resistance encountered. To get charges to move through a material requires the expenditure of sufficient energy to overcome the resistance of the material and to move a charge from one end of the sample to the other. If there's insufficient energy to overcome the resistance, the charge does not arrive at its destination and no current flows. If there's too much energy, an excessive number of charges flow and the sample heats up. Moving charges involve the consumption of energy, some of which are converted into useful work, such as movement, and some of which are converted into wasted energy, namely heat. In order to get the free electrons to move, a certain amount of force has to be exerted on them. This force is called voltage and is measured in volts, the symbol for which is capital V. Voltage is due to the potential difference between the two ends of the sample. We're now in a position to check what happens in practice in electrical circuits. Circuits are made up of resistors through which current flows due to the voltage available in the generator. For the moment, we'll only consider DC circuits. First of all, let's look at the physical aspect of resistive elements. The simplest case is a conducting wire. There are many other types of resistive elements, like the ones we can see. The most widespread are those for high power values and those for printed circuits. In cars, the most widespread resistive elements are incandescent ones for bulbs, those in the heated rear window, and in general, all items of electrical equipment and the cables themselves, which should have a resistance as near to zero as possible. There are instruments specially designed for measuring each of the electrical values which we've looked at so far. An ammeter measures current, an ohmmeter measures resistance, and a voltmeter measures voltage. Nowadays, there's a multi-purpose digital instrument called a multimeter, which can carry out numerous measurements, some of which we'll see later. The multimeter we're going to use is suitable for carrying out the following electrical measurements: DC voltage, AC voltage, resistance up to 20 megaohms, measurements on diodes, DC and AC intensity up to 10 amps, or by using an ammeter clamp, currents over 10 amps and up to 600 amps can be measured. To select the particular function required, the central knob is turned to the relevant position. The multimeter is supplied with two cables, one red and the other black. At the base of the multimeter there are 4 sockets, into which the plugs at the ends of the 2 cables should be fitted. The socket which has a black surround and is marked with the letters COM always represents the common socket for all measurements. The plug at the end of the black cable should be fitted into this socket. whilst the red plug should be fitted in one of the other 3 sockets, depending on which measurement you wish to take. To measure volts and ohms, the plug is fitted into the socket marked with the volt and ohm symbols. For the ammeter function, there are 2 sockets. One is marked A for current values up to 2 amps, in other words, the very small current amplitudes typical of the electronic sector. The other is marked 10 amps for current values up to 10 amps, this being the amplitude normally encountered in car systems. For measurements over 10 amps, it's necessary to use an ammeter clamp coupled to the multimeter. The electrical connections should be made as follows. Position the multimeter selector in the position 200 millivolts direct current. Connect the clamp's black plug in the COM socket on the multimeter, and connect the clamp's red plug in the volt-ohm socket on the multimeter. Position the switch on the clamp marked off, low, high at the low setting for measurements up to 200 amps, or the high setting for measurements up to 600 amps. There's also a small toothed wheel known as a potentiometer on the clamp, and by turning it to the left or to the right, the multimeter's display unit should be set at 0. The equipment is now ready for use. To measure voltage, the voltmeter should be arranged at the ends of the 2 conductors between which you want to measure the potential difference. To measure resistance, the ohmmeter should be arranged at the ends of the resistor. To measure current, all the current flowing in the circuit obviously has to pass through the ammeter, and so it needs to be connected along the circuit itself. When acting as an ammeter, the multimeter must be connected to one of the 2 supply leads, usually the positive lead, with the instrument's 2 leads linked to the ends of the disconnected supply lead. When using the ammeter clamp to measure current greater than 10 amps, it's not necessary to disconnect the circuit. It's sufficient to position the clamp on the lead through which current is passing. We're now going to build up a circuit using special cube-shaped teaching aids. Each small cube has a drawing of the symbol identical to the one with which electrical circuits are represented in technical drawings on its upper surface. Inside each cube is the relevant electrical component in perfect working order. On each side, there are plates enabling it to be connected to other small cubes. These teaching aids enable us to build up working electrical circuits which can be measured and allow us to see how they're represented symbolically. Let's first take the storage battery which supplies voltage, potential difference, which in this example is 12 volts DC, just like a car battery. To this we add small cubes representing connecting wires for the subsequent circuit, and 2 small cubes which represent contact terminals for connecting the measuring instrument. At this point, we begin building up the circuit by connecting 2 small cubes which represent the resistance of the wires. We add a switch, which can be used to open or close an electrical circuit, and by means of other connecting wires, a variable resistor. We now connect the measuring instruments, an ammeter for measuring the current, and a multimeter for measuring the voltage. The probes we'd positioned previously are fitted in the connecting terminals. Since the switch connected into the circuit is still open, no current flows. In fact, the ammeter reads 0, and the voltmeter shows the voltage at approximately 12 volts. We now press the switch and close the circuit. As can be seen from the ammeter, current flows through the circuit from the positive pole of the battery to the negative one. Now we can operate the small knob which varies the resistance value, and note how the current reading on the ammeter varies. We now see the same circuit made up with real electrical components. We have a battery to which we connect 2 electrical wires of equal resistance. We connect a switch to one of the wires in order to open and close the circuit. Now we connect the multimeter into our circuit. one set to volts and the other to amperes. We complete the circuit by connecting into it a variable resistor. To check the value of the resistance, we add another multimeter, this time on the ohm setting, with two wires connected to the ends of the resistor. When the switch is open, no current flows and the ammeter reads 0. The reading on the voltmeter is that of the battery, and we're able to read on the ohmmeter the resistance value, in this case about 67 ohms. Using the switch, we close the circuit, allowing the current to flow. The ohmmeter is self-excluded. On the ammeter, we can read off the current values, in this case 0.18 amps. If we reopen the circuit, we modify the resistance value by reducing it to about half its previous value. Now we reclose the circuit and, using the ammeter, measure the current value. It's now twice what it was previously. In other words, 0.36 amps. At this point, it's easy to see that current, resistance, and voltage are linked together by a very simple relationship. In fact, if we multiply current by resistance, we get voltage. The law we've just demonstrated is called Ohm's law and is written in this form: current times resistance equals voltage. Let's look at one or two resistors on a car and check their effectiveness. To carry out such checks, we use the instrument on the ohmmeter setting, which enables us to check both the resistance value and whether there's a break in the circuit. If the instrument shows a resistance reading infinity, this indicates a break, whereas if we see a definite reading, there are no breaks in the circuit and the resistance is as shown. Let's now check whether there are any breaks in the windscreen washer pump motor circuit. Disconnect the connector. Connect the probes to the supply terminals of the motor. Finally, read off the resistance value on the instrument. Another of the resistors is represented by the leads connecting the spark plugs to the distributor. We use an ohmmeter to discover any breaks. Disconnect the lead from the distributor and connect one probe. Then disconnect the cable from the spark plug side and connect the other probe. If we get a resistance reading, there are no breaks in the lead. Another resistor is the one on the rotor arm inside the distributor. We measure its resistance by resting one probe on the voltage input terminal and the other on the output terminal. The instrument shows us the resistance value. These resistors form an integral part of the ignition system, and their main purpose is to reduce the emission of radio interference from the ignition system itself, thereby improving the car radio reception and avoiding interference with signals for the car's electronic equipment. We check that there are no breaks in the ignition coil wiring by measuring the resistance of the two windings. We measure the value of the primary winding on the two external terminals. This winding, which receives a low voltage supply from the battery, should have a very low resistance. We now change the scale on the multimeter and measure the resistance of the secondary winding. The output from this winding towards the spark plugs will be at high voltage, and consequently a very high resistance value. In this way, we've checked some of the resistors present in the ignition system from the coil to the spark plugs. And that's the end of Module 1 of this 4-part program.